Problem set number 4, question number 6. So kind of carrying on with the same theme of the question that we just did. Here we have perhaps a slightly better curve. This could be the normal distribution or the t-distribution. And the shapes are generally the same. The t-distribution changes its shape depending how many samples you have. That's why we have to be concerned with the degrees of freedom, the number of samples. But the way we deal with these kind of questions are pretty much the same. Ultimately, we just use a different Excel function. So if we remember from the previous video in question number 5, here we have our normal distribution, and we had a little shortcut rule, the 65, 95, 99.7 rule. That rule applies only to the normal distribution, but it is very handy. It says that between -1 standard deviations and +1 standard deviations, so this middle part of the curve, in between those two thresholds, those two boundaries, will contain 68% of the data. I said that a little poorly. So 68% of the data is contained between -1 and +1 standard deviations. Similarly, 95% of the data is contained between -2 and +2 standard deviations, and 99.7 is contained between -3 and +3 standard deviations. So in question number 5, we could do a little shortcut and say, well, 95% of the data is in between 2 or -2 and +2 standard deviations. So here's a standard deviation. Let's multiply that by 2, and great. If we take our mean and we move down 2 of those standard deviations and take the mean and move up 2 standard deviations, that gives us our lower boundary and our upper boundary that contains 95% of the data. That was a shortcut because that ±2 standard deviations is really an estimate. And if we were to use an Excel function or a lookup table, we see that instead of 2, the actual value, or a better estimate, is about 1.96. And this is the function that we used to calculate that for question number 5. We used a normal curve that was standardized, so we didn't care what the mean or the standard deviation was. And we wanted the inverse, or at least what Excel calls the inverse, meaning we're going to give Excel a probability, so how much white space we're going to have left, and it will tell us what the z-score is that will produce that much white space. So how far away from a mean do we have to move to give us that much white space, that much unaccounted for data in this case. For question number 6, really we're just going to do the same kind of thing, but because question number 6 uses the t-distribution, we cannot use this shortcut rule. Again, the shortcut only applies to the normal distribution, and since we are forced to use the t-distribution, we're also forced to use an Excel function. This is the particular Excel function that was taught in class. It's an effective one, but it's not a great one because it kind of breaks the pattern of how we do things using the normal distribution. So I'm a little annoyed at Excel with that. Perhaps you guys are too. But at least it is presented in the lectures that way. So here's how this particular function works. Instead of the normal distribution, we use the t for the t-distribution. Up here we had the inverse, meaning we are going to give it a probability and it will tell us a z-score. Same thing, we're going to use an inverse here. We're going to give it a probability and we are going to get a t-score, in this case, the t equivalent of a z-score. The t-based function for this kind of thing, since we can have white space on the left-hand side and white space on the right-hand side, and I keep saying white space, so we're asking, or the question is asking for 95% of the data. That's the green part, which means we have a total of 5% of the data unaccounted for. And that 5% of the data could be down here, and or it could be up here. So ultimately, we're going to take that 5% left over and divide it in half, so we have 2.5%. And we're going to assign 2.5% down here and assign 2.5% up here, because we don't know where the data points are actually going to go. And assuming the data are actually distributed following a t-distribution, half of the data, half of that 5% should be down here, and half of the 5% should be up here. So when it comes to the t functions in Excel, we have to specify that we're going to take the data, divide it in half. We're going to do effectively a two-tailed test by specifying that dot to t. So that's great, except instead of having this really high number for a probability, now we're going to have this really low number. So for the dot to t function, Excel wants to know what the total amount of white space is, and it will divide it in half for us. That 2 has nothing to do with dividing it in half. That 2 is the number of degrees of freedom. If you remember, for a t distribution, the degrees of freedom is the number of data points minus 1. So here we're talking about historical data. So we have 3 data points. Minus 1 is 2. And so that 2 controls, not that we would see it, but it controls the shape of the t-distribution, and as well, it controls how far away you have to move away from the mean in order to get a certain amount of probability outside of that. So when we plug these numbers in, we use the t.inv.2t function, and we feed it not a big number, but we feed it the small number, the leftover probability. So 1 minus 0.95 is 0.05. So we give it that, and the degrees of freedom, number of data minus 1. Excel will tell us that our critical value is 4.3. So let's take this opportunity to talk about a critical value. What is that? So a critical value is a threshold. That is a single number that tells us how many standard deviations or standard errors, but for now we're just talking about standard deviations. So how many standard deviations from the mean we have to move away in order to have some specified probability outside of that. So that might not have been particularly clear. For this particular example, we're looking for 95, or yes, we want the thresholds that contain 95% of the data. In a normal distribution, we know that's 2 standard deviations, but t-distributions are not normal distributions. We have a very small degree of freedom, so our t-distribution is actually quite a bit fatter than this, so it does something more like that. So it has much larger tails, if you will. So that means in order to get 95% of the data, we have to move extra far away from the mean. In fact, we have to move 4.3 standard deviations away from the mean in order to get in order to have 2.5% of the data over there, and to have 2.5% of the data over there. So in the normal distribution, we only had to move 2 standard deviations. For a sample size of 3, degrees of freedom 2, we have to move 4.3 standard deviations away. So there's 1, 2, 3, 4, and a bit, and minus 1, 2, 3, 4, and a bit. So that critical value now tells us, again, how many standard deviations away from the mean, so this line here was our mean, how far away we have to move from the mean in order to have whatever our specified probability was left. So we wanted a total of 5% left, and that 5% still has to get split evenly on both sides. So we have 2.5% over there and 2.5% over here. So we have to move out 4.3 standard deviations away in order to have 2.5% on the outside. That's what the critical value tells us. It's just that threshold. How far away do we have to move? So that's all of that. Now we have the equivalent, kind of the t equivalent of our 2 standard deviations. Now we just have to do the calculations. So what are the actual limits? Our ultimate formula is still kind of the same. We start at the mean, and we need to add we need to move 4.3 standard deviations out, and a standard deviation is still 13.9. So we take 167, the mean, plus 4.3 standard deviations away times whatever a standard deviation was. That tells us our upper boundary is 226. And the lower boundary is the mean minus the 4.3 standard deviations we have to move times the value of a standard deviation, and that gives us a lower boundary of 1.07. Hopefully that made sense.